hopefully you've had plenty of coffee because I'm going to rip into it. And you're going to get plenty of information thrown at you, but I'll be around for the rest of the day if you need to get into it. So I want to go through genomics, add value and precision. And I want to meet the conference challenge. So the organisers of the conference have put out a challenge, and hopefully I can meet that challenge. We're going to have a little look at genomic selection and how we make it work in beef. What are these single-step genomic evaluations in breed plan? And Christian's already given us some background, so that's certainly helped. What are the latest validation results? So this is some work we've done. Is single-step working in Angus? What's the importance of your reference populations? And if Sinclair hasn't cracked me off, where do we go with Angus? And we'll take some questions. So the conference challenge was to encourage producers and industry professionals to delve beyond the beef to ensure they are future-proofing their production systems and remain at the forefront of the industry. And I've pulled that apart because I think that's the most important word there is future-proofing, and genetics will be essential. So in the future, genetics, you are genetics, it's the future package of your genes is held in this room in your care. And we've got to make sure that we match that with future production systems, markets, consumer and society requirements. And the other one is forefront. And again, genetics are going to play a key role, at Angus being in the forefront. A clear breeding direction where you're plotting your course, and you're going to need all the tools to be able to make sure you're at the forefront. Tools, traits, balance in selection, new methods and adoption. And so, to me, that's going to occur through having state-of-the-art genetic evaluations and then breeders actually using it to make change. And what's state-of-the-art? So I pulled up Google, and state-of-the-art is the most recent stage of development of a product, e.g. breed plan, and incorporating the newest technologies, ideas and features. So to me, that's what we're looking to do with what we do in breed plan and also in TACE, is make sure that what is available to producers is state-of-the-art. So the development of the genetic evaluation, why do we do it? We want to describe genetic differences between individuals such that commercial industry can match those genetics to production systems and markets, and so our seed stock sector can make genetic change. How do we do it? Well, currently we've got the breed plan system, which is an evolving science. We do new models, new methods, new traits, new data sources, and obviously now genomics. But it's critical, all these developments, is that EBVs predict phenotypic differences. We just don't make change for the sake of having another EBV. And as Christian outlined, it's really critical that we make sure that these EBVs are predicting differences in progeny. So we've seen some big changes, and 86 is a real seminal year in what we do. Who was born after 86 in the room? Yep, plenty of people. Well, that's what I looked like in 86. And now here we are at 2003, nearly 40 years ago. But also we can go back in time, and I won't give you the exact date there, but I used to look like this. Now what happened in 86 was where things changed, and I was probably, I don't know, just finishing university. You got your first sire summary, and there it is there. And it's interesting to actually look at the books, look through the sires that are in there. So that changed what Angus did in terms of genetic evaluation. Back when I was growing up, that was the only way you could assess genetic merit. And obviously by the look on my face, I wasn't very thrilled about that, and plotted my course for the rest of my career. And now, in 2023, we can pull it up on our iPhones. Back in 1986, it was put out once a year. There was about 500 bulls published in that sire summary, and there were 4 traits. Now, through the TACE, it's every 2 weeks, as Christian showed us, 2.8 million animals and 24 plus traits. So that's the progression of genetically describing Angus cattle. And as you see, it's a very much an evolving science. And we're all getting older as well. So the recent revolution is the advent of this whole genome chip, which came from the Human Genome Project in the early 2000s. We take the DNA, we put it across one of these fancy chips, and we get thousands, tens of thousands, if not hundreds of thousands of results, 0, 1s, 2s, across the whole genome. And that allows us to do all sorts of things. Genomic breed composition, genomic inbreeding, discovery, genetic disorders, cause of mutation, and even gene editing, DNA parentage. But what I want to focus on is we can use that into genetic evaluation. And specifically the Angus breed plan component that Christian showed us. I'm not going to touch on the other ways that we can use the genomics in the genetic evaluation. So I want to show you what we've done now in the genetic evaluation in terms of the breed plan single step. So genomics has massively changed what we do in breeding, and particularly in the Holstein. In 2008, they got access to these chips, and you can see their genetic trend in that blue line just took off. Why was that? They genotyped a whole lot of Holsteins, and the genomic data on young bulls is as if they've already got somewhere between 25 and 140 daughters measured for milk or for the traits when that bull is only 12 months old. So that's increased their selection accuracy and smashed their generation interval, and therefore they've really ramped up their genetic progress. And all they did was use that 50K chip. It was cheap. We now have thousands of markers associated with the trait. They include that in the EBVs, and they can select those young bulls more accurately. So what have we got to do in beef? We've got to record those records, we've got to take SNP profiles, and we've got to make sure we've got suitable genetic evaluations. And this is what's called a reference population, is those animals that are recorded and also genotyped. In beef, we don't need genomic selection for weaning weight or scrotal circumference. It's really these hard to measure traits, particularly ones you can't do it at home, on the farm. So they're economically important but hard to measure. That's where we get the most boost from genomic selection. So if we can get those genotypes and phenotypes, then we can build our reference populations. And simply that reference population, you measure those animals, you take the DNA, then you have a target population. You simply can pull DNA, put it into a genomic evaluation and get EBVs. And that's the power, and that's what we hope to be able to achieve. What drives the accuracy? You'll see later, it's the size of the reference. The bigger the reference population, the more genomic accuracy, and the relatedness to the reference. The more you are related to that reference, again, the more accuracy. So larger, you explain more of the genetic variation. If the reference is small, then you need to be closely related to it to get the benefit. So we've been using DNA in breed plan for a number of years. You had Jason here yesterday. He started off in the whole Gene Star revolution back in early 2000s. Then we started getting the genomic prediction equations. A lot of DNA companies came on board and we started blending those into EBVs. Then we got the whole chip, and then 2017 we developed the single step analysis and moved on even now as it grows to having modifications on that. So single step breed plan, it is state of the art. Developed in 2017, it simply replaces the pedigree on animals with their genomic relationship based off the SNPs. This picks up the genomic contributions to the trait in one step. That's the real key. We don't have to do discovery, calibration, validation, etc. The single step is doing that for us. Also, we include non-genotype. We have lots of animals in our pedigrees that aren't genotyped. We can't simply throw those away. So we have to be able to have genotyped and non-genotyped. We need it still to be full multi-trait to have all the bells and whistles that we're used to. But again, EBVs are still EBVs. It's critical to check that they're performing as we expect. As Christian has shown, the genotype in Angus has been almost exponential, such that we're now 250,000 going in to that genomic analysis in breed plan. which is no mean feat. So how do we validate them? Well, we're using the latest statistical LR method, Lagar and Reverter, and someone mentioned Reverter before, so he's actually here. So again, if we've got any curly questions, I can spin them over to Tony. You don't need the individual EBV accuracies, which is always nice because they're already just an approximation. So when you're doing a validation, you're really sort of hamstrung if you've got to rely on accuracies. This one adjusts for the relatedness of the validation animals. So all we do is cut off the records of all animals born past 2017. We get rid of their data, and that becomes the part data. And then we compare it with the EBVs from the full data. And that allows us to validate how is our analysis going. And then we can contrast the part and the full. We can run it as just a normal pedigree analysis, or we can run it as single step. And that allows us to do a forward cross-validation on the most important crop of animals in your breed, which is the animals born in the last sort of 5 to 6 years. So we're saying how good are their EBVs coming out of these analyses if we have single step versus if we just did it as normal pedigree. So just to give this as a visual, so we've got the full analysis with the pedigree and the phenotype going in, then we've got the part analysis, and we simply, in 2018, we cut that data off out of the analysis. So we get rid of the birth weight, so we get rid of the scrotals, or we get rid of the IMF. And then those animals become the validation animals, so all those older animals since 2018, and we take their EBVs and we compare them to their EBVs when they came out of the full analysis. And the animals in the part, their EBVs is driven by the pink box, which makes them mid-parent EBVs. So that's the first run. The second run, we do exactly the same, except we now add in the SNP data in terms of single step. We do the same thing. We cut that data off. We get their EBVs from the full run. This now becomes the training set, all the genotyped and phenotyped animals for that trait, and these become then a test of how good are the genomic EBVs. So hopefully that was straightforward. This is the sort of numbers involved in the validation. So that's the number of animals genotyped with each trait, birth weight, weaning weight, etc. In the green, they're the validation. And then the blue is all the other animals that operate as the training. So you can see you've got lots of data, not so many for your mature cow weight. If we go to the carcass traits, you can see here the number of training animals now is only in the 4,000s, and the number of validation animals are smaller, and that might explain some of the results that we do see. And again, days to calving is low, and as Christian shown, the net feed intakes. So these results are premised on the reality that we have different numbers of records. What do we get? We get accuracy, we get bias, and we get stability as a way of measuring the metrics as to how well are we doing. This is simply how close is the estimated breeding value to the true breeding value. This one is 1 unit of EBV generating 1 unit of phenotypic difference. And this one is how much does the EBV change when you add more records? And that's simply, is this adding value? Is this adding precision? And is this adding precision? Which comes back to the title of the talk. So here's the money slides. If we look here, we've got pedigree in blue, single step in the red. This is the accuracy of the analysis for those animals in the part from the single step run and from the pedigree run. And for these traits, you can see we have a very big lift in the accuracy of those EBVs from single step compared to the pedigree run. If we then look at the scan traits, the carcass traits, and the fertility traits, you can see all those red lines are considerably above the blue line, showing that the accuracy of these evaluation of these EBVs is significantly increased through these single step runs for those 2018 and beyond animals. So single step is generating higher accuracy. You can see the days to calving. It has the least improvement, and it has one of the smaller reference populations, and likewise the NFI is the lowest. So again, if you don't have the data, you don't generate the improvement. We've actually done this across all the breeds that do single step, and you can see Angus is sitting there averaged across all your EBVs. There's about a 26% increase in the accuracy from the single step, but also we're seeing significant improvement in all the other breeds. So single step is increasing accuracies across all the breeds, and we've done this work recently for those breeds. Where's this coming from? If you plot all our breeds and all the traits, you can see as the size of the training population goes up, the validation accuracy increases. And it's a very, obviously it's noisy, but certainly bigger reference populations, more accuracy. If you put it on a log scale, you can see it's pretty clear that as the populations get bigger, across all the breeds, across all the traits, you get increased accuracies. So we need to be looking at these reference populations. The other statistic was bias. So we expect for 1 unit of the EBV, we're getting 1 unit, and you can see even for pedigree, we're doing a really good job in all our traits, if you look across there. But again, the red bars are closer to 1 than the blue bars. So again, we're getting very unbiased or very good estimation from that single step run. There is a slight over dispersion from the carcass traits. We get a little bit more phenotype than the EBV predicted, and that's something we'll look at, but it also could just be a function of those lower numbers. And finally, this is the last one, is the stability, and this tells us when we add the phenotype in, how much does the record change, or how much does the EBV change? And so what we want to see is that when you add the data in, you don't get all the fluctuations in the EBV. So you can see, again, single step is creating more stability. There is less change in the EBV when we add that record in. The only trouble with that is you get decreasing influence of the animal's own record. And this is what people tell me. I put my genotype in, and then I scanned, or then I put a birth weight in, and the EBV didn't change. And that's because you're working with traits in Angus where you've got large reference populations, and the genomic accuracy is already giving you a very good accuracy. And so that's a bit of a dilemma that we're faced with now, is that single step is certainly increasing the stability of the EBVs, but it does mean you get a reduced impact of the animal's own record when you submit it. And I've just pulled that apart a little bit for birth weight. So this is what you see for those 123,000 animals. That's what their plot of their pedigree EBVs are. And when you run single step on exactly the same animals, you see that we're spreading them out more in that analysis. So we've got more spread, which allows you to have more genetic progress. They're more correlated, which gives you more stability. And the regression is closer to 1, there's less bias and more precision. So really clear that the single step analysis is doing its job. But with that, something like birth weight, if you've got, that's what the spread in EBVs are for those animals when it's single step with no record. And with the record, we don't change that population very much. So when we put those records in, the EBVs are already close to what they are when you put the phenotype in. And so this is a case where people say, should I be measuring birth weight because I don't see a lot of change? So you can see there is a slight increase in the spread, but there are some bulls, when you add the phenotype, that their EBV has gone up by 4.5 and some have dropped 4.5. So they do change. But when you've got traits like net feed intake, which only has a very small training population, when you run single step, that's the spread in the EBVs of the bulls. Without it, you give a very big spread. So the influence of the data is much greater. And you can see there are some bulls going up by as much as 1 and 2, 1.5 kilos of net feed intake. So again, when you've got lower stability, when you've got lower training populations, the records do change the EBV more. Righto, so just to finish up, accuracy can certainly increase, but then it's got to be put across what is the cost of recording. We see that we get different utility of records, as we just saw. Some records are going to give you more influence on your EBVs. If we don't get those phenotypes, we get erosion of that genomic prediction over time. And if new traits come on board, you need to be recording them. So this, should we be recording, should we stop recording? You know, they're key. So genotyping Angus certainly is very good value, but who does the recording for the Angus reference? And this came up in the panel this morning. Should individuals be carrying that load? Should there be collective recording through your SIRE benchmarking? Who should be paying for that? And who benefits? And I think those 2 points in blue, they're relevant to all breeds, and everyone is wrestling with that. Who should be paying? How do people get remunerated for their efforts? And who's getting the benefits? So the genomic selection is almost, you know, we've got to be careful what we wished for because it's now here, and we've got to now work with where do we go into the future. So the structure is important. If you looked at those graphs, any trait that's got less than 10,000, we need to be working hard to get them up. So anything under 10,000, we really aren't getting the benefits of genomic selection. If the trait has a low heritability, we're going to need more records. If you can measure with more precision, then you need less records. So making sure in the abattoirs we're using the very best technology. We need to be focusing on those difficult to measure traits. And if your reference is small, then you've got to be well related to it. So building the Angus genomic reference, which is what's going to future-proof you, I think your current traits where you need more effort from what those graphs are telling us is you certainly can benefit from more abattoir carcass. We can lift the accuracy of carcasses by building the reference. Cow traits are underdone, in my opinion. Fertility, function and feed. And we need to think about how we get those records because they're the ones in that graph that were struggling. And also we saw that feed intake and efficiency. So they're to me current traits that really need to be focused. What about some future traits? You heard from Sam yesterday, methane. We've just seen some eating quality, the resilience in terms of immune competence. I think, you know, a lot of my research is on female and male reproduction. I think there's opportunities in Angus as well to lift those for the future. And we've talked a lot this morning about consumers, making sure that we're measuring the traits that allow us access into markets, welfare and healthfulness of our beef. And they're measures that we have to be taking in a population somewhere in Angus. And then those genetics have to be, what are the genetics that we evaluate in those programs? And I think we've got to look at, are there current popular bulls that have got lots and lots of progeny? How well are they covered? Are there young guns that are emerging that in 5 years' time are going to be the future? They need to be measured for these traits and new traits. New US bulls, you know, what structure is in your ASBP to make sure that your genomic reference is covering. And so they're just some pointers I had in that regard. And just to finish, to keep you at the forefront, certainly we're going to have improved genomic evaluations and they'll be moving more and more towards multi-breed. We're going to need better data that will generate better and more EBVs. So there'll be more EBVs coming. We're going to see improvements in the SNP chip, which will show benefits as well. Most importantly, we need very clear breeding objectives because genomic selections allows us to get there faster. And it could be faster in the wrong direction. So we've got to really be clear on our breeding objectives, otherwise we could go down the wrong path at a much faster rate. And with genomic selection, you also increase the ability or the capacity to have increasing levels of inbreeding because we, again, are focusing and therefore you have to be managing inbreeding at the same time in making these selection decisions. And of course, nothing works unless people use those EBVs to make change. So we've got to be getting adoption, and we heard about, you know, people in Alice Springs, we've got to make sure they understand how to use EBVs. And just, here's a bull. Anyone know who he is? Scotch cow. So a lot of people, 1982 bull. And so we can make all these improvements, but the most critical thing is we must have stable genetic evaluations. So I pulled him out, and I've got a couple of these sire summaries around if anyone wants a bit of history lesson. He first came out in the early 90s, and he was published in the 1992 summary, and he had 4 EBVs, and there they are. And I pulled him out of TACE this week in 2023, and you can't quite read that, but he's 6.5, 35, 68, and 84. So that's, to me, is what you need to be able to see is you can make all the changes you like, but you must have a stable genetic evaluation, and I believe this is good proof. You'll find some that didn't do this, but there's plenty of them that are just like this, that even though we've made all these enhancements, we still are ranking these bulls, and your genetic trends over time are real. So breed plan is state-of-the-art, increased accuracies, low bias. There is much more opportunity for genetic progress, up to now 25% increase based on those accuracies. You can do more balanced selection because you have higher accuracy for the difficult traits, which previously were low accuracy. You need to do the SNP profile first. As soon as those calves are registered, if you put those SNP profiles in, you're going to get more stable EBVs. You're not going to see the fluctuations that you see with putting records in and then doing the genotype and then putting more records. If you can get the genotype in first, then that's going to give you more stable EBVs. And then your genomic selection is going to rely on the size of the reference, the structure of that reference, and doing selection with a goal. Thank you.